So Luis is going to circulate the blue sheets. Yeah. Okay, great. As far as if people want to move closer, please do. Some will be coming in. This is a complicated time zone for some of our speakers, so we're going to have the folks who are here go first, so they have a little time to have more coffee or tea. And I'm Jane. I'm one of the co-chairs of Gaia. The other co-chair is Arjuna, who is currently at Cambridge University and hopefully waking up. So the blue sheets are going around. You need to sign in. Please take note of the note well. We have 3 remote participants, and they'll go next. I'll put the agenda up in a sec, and give me another minute. So, as far as our note takers go, Corinne, Amresh, and I are both going to trade off, but Corinne's up front. Thank you very much, Corinne Kath. Amrish Foker from Afrinique, who's going to be speaking first, is also a note taker, and Jane will also be back up. Blue sheets are circulating. Please sign in, and I'm going to go through the agenda in about 30 seconds. So good afternoon, everyone. You are in Gaia in the Olivia room. Thank you for joining. This is Global Access to the Internet for All. I'm one of the co-chairs of Gaia, Jane Coffin from the Internet Society. The other co-chair is Arjuna from Cambridge University, and also now with the Amber Laboratories, and he'll tell you about that when he speaks. So our agenda, first up, is for me to give you as little data as possible that's not relevant to this discussion so that we get on with it. Does anyone have any quick questions before we start? But Amrish is going to start with this awesome presentation on dissecting the African internet. After Amrish, we have Luis Martinez, who's the president of the ISOC chapter, but also a researcher and technician who works in Mexico with community networks, and most recently did some amazing work with the disaster relief with the earthquake in the Oaxaca region. After Luis, we'll have Arjuna up. After Arjuna, we'll have Leandro, who's from UPC in Spain, also working with the Amber team. And after that, we'll have Jehan. It's all on the agenda online, so please make that available to all of you. So I'm going to turn it over to Amrish. Each person has 15 minutes, generally about 12 for speaking and 3 for questions and answers. We'll also do some Q&A afterwards. So, Amrish, you're up.
All right. Thank you. Yes, so my name is Amrish. I work at Afrinique as a research manager, and today I'm going to talk about a latency study that we've done wide scale on Africa. We are not going to talk. I'm not going to talk about community networks, but I'm sure my colleagues will give you a lot of information about community networks. But the importance about this study is how we are actually how we can actually understand the bottlenecks in the internet in Africa and how possibly we can overcome them. Right. So. Maybe next slide. So what do we know? We know for a fact that, for example, in Africa, first of all, internet in some places are extremely expensive. For example, in South Africa, where I live, to buy 1 gig of data is around $15, and here I actually bought 100 gig of data for $15. So there's quite a big difference. And now you can actually imagine people living in rural places where sometimes they can actually use up to 20% of their income to buy internet products. Actually, other thing that we know is that peering is quite poor in Africa, and this is what we are going to show through this study. And what we are seeing is a lot of circuitous routes. So basically two networks in Africa trying to send packets to one another. And what's happening? We are using very expensive international links. Next, please. So the research question is, we wanted to know how are countries closely related in Africa, because this is important. For example, if we want to attract content providers to come and install their cache or CDNs in our region, right? We want to keep traffic local, as I said. So we wanted to understand how does it look like? How are countries close to each other in terms of latency? Next, please. So obviously, to do internet measurement type of study, we have a very well-known platform, which is RIPE Atlas, which is quite well spread around the world, but not so much well spread in Africa. And there are around only 229 probes covering 36 countries in Africa, which is not that much. On the other hand, there is another platform called the Speed Checker. Unfortunately, it is a proprietary platform, and but the good thing about it is that it is quite well distributed, more than 800 probes in 52 countries, so basically giving us a coverage of more than 50% of AS numbers. Next, please. So this is what I just said. A very good coverage of the speed checker probes. Obviously, the only issue with speed checker is it is a software-based probes as opposed to a hardware-based probe, which RIPE Atlas is. And then the fact that it is a software-based probes usually installed on end users' devices, it fluctuates. Sometimes it is live, sometimes it is off. So the reliability of this of the platform is quite less as compared to RIPE Atlas. Next, please. And then, of course, to measure latency, we need a target. So we chose speed tests, not net targets. Speed test is very well known. You usually do UCLA test. Those are the test servers that are the targets that are being used. We had 213 speed test servers spread around Africa in 42 different countries, and we use them as targets. Next, please. So we did a lot of pings. So we were actually randomly choosing the targets and then launching the pings, and then obviously to know how many hops do we have in between the different the different endpoints. Then we were launching traceroute. We then use this data to on the RIPE risk database, and we also use geolocation using MaxMine to know where exactly the vantage points were. Next, please. So the data collection we did was over 3 months, 4 times a day. As I said, pings and traceroute. We got more than 42,000 RTT samples and more than 31,000 traces. And the coverage was quite good, actually, 319 AS numbers, which we thought was quite representative of the African region. Next, please. So this is what we got eventually. So basically what we had was, what is the latency between country A to country B? And we got this very nice matrix. So we did, of course, we calculated the mean of the latency. And if you see the diagonal line on the matrix there, you will note that you can have a straight blue line. So which means that latency in those between the same country is more or less fine, meaning that perhaps IXPs are actually working in those countries, but you have some countries, for example, DR Congo, where you have a very high latency, and this actually triggers question, or do they actually have an IXP in that region, or if they have an IXP, or the different networks in this country peering or not. So if we calculate the mean in Africa, it's around 78 milliseconds in country latency. In the Latin American region, it's 76 milliseconds, which is quite comparable. But if you have a look to North America and Europe, they are actually many steps ahead of us. Next, please. So a few countries were actually performing well in Africa. Those are Mauritius, Réunion, and Côte d'Ivoire, where the mean latency was under 30 milliseconds. And under 40 milliseconds, just above them were South Africa, Egypt, and Benin. But the funny thing is that some neighboring countries, well, I've put the ISO code below Zambia and Malawi, or Zambia and Zimbabwe, or here Mauritius and Madagascar, two countries that are actually connected using undersea cables, or Mauritius and Réunion Island, which are very close to each other and also connected using undersea cables. The latency were very high in between those countries. So why is that? Because intuitively we would say that neighboring countries or countries very close to each other should have technically low latency. Next. So once we got this matrix, what we say, let's do some clusters, and we use an algorithm called the Louvain algorithm to cluster the countries together, and this is what we got. We got 4 different clusters in Africa: northern, southern, eastern, and western. So you would say that this is kind of expected, right? Next, please. This is kind of expected. But you will see some particularities, which I'm going to explain now. Next slide, please. So the unusual cases, for example, if we have a look at West Africa, Senegal, Liberia, and Benin are on the west coast, actually are in the northern cluster. You see the yellowish countries are in the northern cluster instead of the western cluster. So why is that? Why is that different? They should normally be in the same cluster as neighboring countries, for example, Côte d'Ivoire. Next, please. That's another good example. Madagascar, Seychelles, and some other Indian Ocean islands are clustered with the northern African countries. So basically, it means that it is faster to send packets to Morocco from Madagascar than to send packets to South Africa. So yeah. And finally, we had another case here, Somalia, which is on the east coast, is clustered with countries which is on the west coast. And you would think that Somalia has no link really with the Western Africa. So those are the particular cases. And then we have, next slide, please. 2 countries which were actually unclustered. So it means that the link characteristic, actually the latency were so high for those countries that they couldn't be clustered in any clusters. So why is that? So first of all, Ethiopia as a country has most of the upstream, actually all of the upstream providers are international upstream providers. So no traffic is being sent locally. It is more or less the same case for Angola, where 60% of upstream providers are overseas. 5 minutes, okay. So if we have a look at the different intercluster latencies, we see that Western Africa is actually the worst, and Southern Africa is actually the best. So why is that the case? We found out that, for example, in Southern Africa, there is a very good peering fabric, and Western Africa actually is lacking behind in terms of in this regards. Next, please. Yes, next. So if we have a look at the upstream, so we plotted a very nice graph of where the upstreams are coming from. The bigger the dot is, it means that the more upstream you will have for this country. You can see that South Africa is actually a very dominant actor in terms of upstream provider in the African region, but most of the countries are actually peering with overseas upstream providers. Actually, more than 37% of trace route actually had their first hop outside of Africa for all the measurements that we did. Next, please. So this is just a list of the top 10 upstream providers, and next you will see we have a few which are actually African: Seacom, Liquid Telecom, MTN, and Telkom SA. And we also found out that, for example, in West Africa, where situation is not that good actually, France Telecom is actually very well present over there, with more than 17% of the French-speaking countries. Next, please. So this is just an illustration of how many hops do you have in between if you want to send packets from one cluster to another. Basically, more than 50% have hops going outside before coming back again to the same cluster. Next, please. So basically, what we've seen is that if you want to send packet within the northern cluster, the average speed is 71 milliseconds. From south to north, this is quite bad, 227 milliseconds. And generally, what we found is that within the same cluster is more or less okay. If you want to send packets to another African cluster, it's higher. And if you want to send packets to overseas, it's much more higher. So takeaways: some countries are performing well, as I mentioned, but some countries are really relying a lot on international transit, which is mostly the Western African countries. And I suppose we need to work more to increase the peering fabric in those countries. And that would actually help bring content providers and CDNs and people like them. Next, please. And yeah, so the implication for the global access for all is obviously this type of study can help improve access. If we improve, as I said, the peering fabric, then we can reduce cost, for example, and yeah, as I said, attract more local content and CDNs and caching players. Thank you.
Fabulous. Any questions for Amrish? We have time for one or two, and we'll hold for after the other presentations as well. But please let us know if you have questions. Please.
Hello, this is Niels ten Hoever. Thanks so much for this fascinating research. Could you perhaps give us some insights into the reason for 100% of Ethiopian internet traffic going outside of the continent?
I don't know exactly why the reason. Sorry, we can guess. Maybe you know the answer.
There's one monopoly provider that,
Okay.
or let's just say there's no competition.
Okay.
There's no IXP. There's one mobile operator, one fixed operator, and they're managed by the same entity, same organization. And that's likely to be part of the challenge. The other thing is cross-border connectivity. Among a lot of countries that are landlocked, those border agreements are complicated. Some countries will charge VAT on the traffic going from country to country. We've seen this in Latin America. We're seeing it in parts of Africa, where those cross-border agreements are really important between countries to get out to the sea so they can move the traffic out to bigger pipes. And satellite connectivity is crazy, so it's really expensive.
Right. Thank you very much.
Any other questions, quickly? Well, bear this in mind. There's been a lot of work through Afrinic and other organizations to build internet exchange points. We always welcome experts from IETF and other to work with us on some of those workshops. So you can touch base with Amrish, me, my colleague Machuki as well. We do this work around the world, and it's really important. And so do organizations like Packet Clearing House. It helps with access and bringing latency down, local content exchange locally, and also just sometimes it's a lot cheaper to exchange locally than the long haul traffic costs.
Right.
Cool. Thank you.
Thank you.
So Luis Martinez is up.
Ready. Hi. Yes, it's working. Hi, good afternoon. My name is Luis Martinez. I'm coming from Mexico. And I'm going briefly talk today about how we have bring the knowledge that we have got from the community networks, the way we deploy the community networks into the disaster relief in Mexico City. Yes, we tend to believe that community networks, they always are in a rural environment, that they are for poor areas, but no, community networks happen in a number of environments, very different, with many different technical challenges, that this one was a good opportunity to show the usefulness of such developments in disaster relief. So, whenever there's a disaster, there are 4 phases: what you do before, what you do during, what you do just after the event, and finally, when you finally recover from the event. That will be that the disaster will show you how well prepared you are. That will make a stress testing on your infrastructure, and you will learn that not everything can be foreseen. Yes, you're always missing something, and you need to develop the way to quickly implement solutions for that. Yes, nobody thought that the mobile phone antennas were going to fall down. Why? Because they were in buildings that were supposed to be solid, but nobody had in their mind that there were going to be 2 earthquakes coming from opposite directions and meeting at Mexico City. That made a very, very different scenario. Also, in the south of Mexico, in Oaxaca, there was a large earthquake, which also brought many things down. And still today, they're having replicas, or they're having the small tremors about 5.6, 6, some of them, which are still considered earthquakes. Yes, so that day in the morning, there was a drill for the being prepared. We have been preparing 30 years for the same scenario, and it happened again in the day that the last big earthquake happened in 1985. So that was the same scenario, different conditions. Next. So this scene is from Oaxaca. Yes, you never thought those things were going to fall down. But even when they fall down, everybody thought that the infrastructure was going to be affected, because in 1985, we couldn't make any phone call outside of Mexico. We had to use RF links, VHF radio messaging. There was not useful internet for that. So now with the internet, things change. So as I tell you, you need to quickly develop or unveil the plans you have for communicate. Why? Because it's most likely that the voice infrastructure is going to fail. Why? Because we are designing circuits to handle data optimally, not voice. Then data was okay. Everybody was using personal messages to tell the other ones that they were okay. But some people found out that they were able to send pictures, send videos. So that made things a little bit more complicated. Then on one side, the army was implemented their plans. Yes, nobody knows their plans, but they were implementing the plans. Then the civil society organized themselves around the social networking. Yes, and the local government had other plans. So that's when it came the first response can be anyone, but quickly needs to be coordinated to the other ones. And that happened through the internet. Yes, very quick. A lot of people put effort into a tweet about the places where the buildings were falling. From the first picture, what you see of dust were the fallen buildings in Mexico City. We're talking about a city with 23 million people, so it gets quite complicated. It happened in the city center, yes, and then the young people started a map, and later they got help from Google and the government to pinpoint where the buildings were falling. Fortunately, NASA had a satellite, so they were able to detect variations in the height of buildings about 30 centimeter. That map came out with a precision of 95%. So they were able to locate the areas where there was a building that fell down. And the results could be far worse, maybe thousands of people dead. That death toll was about 500 people. So in terms of the magnitude of disaster, could be very bad. Next, please. So what do we know from community networks? I think we have 4 key solutions. One, the first is we build infrastructures very resource-wise. Why? Because we have limited resources. We're always fighting to get a cheap equipment. We are looking to find for grants. So we always work with limited resources. We always work in hard-to-access areas, such as in an earthquake. That happens. Yes, everything becomes hard access. So you need to rely what you know how to work on the urban areas. We build lightweight solutions. Why? Because we need to bring this equipment into these rural areas. So we need to bring the less weight as if we're climbing a mountain, even if we're going flat soil. We are used to fast development. Why? Because we are engineers with a lot of experience in networking, but we're going to areas where we have no resources. We don't even have a screwdriver so we need to implement things on the road. So we do things fast, because also we have 2 principles that come from systems engineering. One is the holistic, that just adding is like multiplying. The other one is the simplicity. Simplicity brings robustness into your designs. And finally, the low maintenance. Yes, we go engineers, we set the community networks, but we cannot go back every time that the network has a problem. So we need to teach people, that community, that their network has to be maintained, and when and how you can call an engineer, not just to say, this light is blinking, what do I do? Yes, so then it's a cultural shift. Next, please. So which are the solutions we provided? We first started with the census. We started looking at the places that needed help. Yes, we were working with these guys that I mentioned later, which are Verificado 19S or B19S. I'm going to explain that. While people in the Mexican chapter were asking what to do, what solution to provide, we got this idea to bring what we know from community networks into the disaster areas, into the shelters. But we need to design a fast solution. So we built a solution in a box, which is a router, an access point, and some battery packs with solar panels. Yes, so we can place them into the shelters and provide access to the internet to guys living in the shelters. Later, we knew that the big telephone companies started to provide free internet access, and they were competing who was going to provide the most free access to the internet. But as it happened one day, 2 weeks later, they just closed down the faucet, and it was over. And our solutions still provide some sustainability. Yes, the shelters is like working in rural conditions. Yes, you have no power, You have a lot of people wanting to connect into the internet, and you cannot go back to the shelter every time you need because there is no means to get there. So on the other hand, we provided advice on this wise use of the internet. We were sending 3 key messages. One, communications are essential in disaster situations. Number 2, just communicate when you need to communicate, not just because you are not having nothing to do, so then you're going to communicate. The third is avoid sending multimedia rich messages. Stick strictly to text, because that is going to lower the performance of the network. And the fourth is only transmit real and verified information. Yes. Why? Because we saw people sending videos, pictures from disaster areas, which can be interesting, but it puts the reliability of the network to -0. People start using sort of walkie-talkie applications. Yes, they use this Cello application, so they were transmitting the needs. But what happened? That many people heard the need, and the need will be, or the aid will be multiplied by 5, 6, 7 times. So we started to timestamp the messages. Yes, very important to put who placed the message at what time, and if it was verified. So even today, in other emergency situations, people are timestamping the messages. So we're going back to the origins. And this effort, which is called B19S, is the result of a number of young people using their social media skills to place key messages to the people wanting to help. Yes. On behalf of the Mexican chapter of ISOC, we gathered volunteers. We talked to the telecom operators. So they provided volunteers to bring hands into the disaster areas. We were not asking for equipment. We were not asking for money. We were asking for hands to help. Because at the end, community networks is that we're talking about people, solutions made by people for people. Thank you very much.
Wonderful. And Luis was super fast. Does anyone have any questions for Luis? Community networks and with disaster assistance.
Really, it was fast.
Stefan Bartsmeyer, AFNIC. A question about the all-in-a-box solution. It was designed before the disaster. During the disaster, you had no time to create it. So it was something done how long ago and by who?
Yes, what we did is take what we usually do in a community network. That will be a point-to-point link, then one routing solution, and then access point to provide service through Wi-Fi. Yes, that will be the cheapest and easiest solution, but we need to put that inside a box. Actually, we put it, I don't have it here, I just have the image of one router we placed in a disaster area, but we put these three things plus batteries inside a 4 inches pipe, PVC pipe, so it became a Wi-Fi totem. Yes, and we had the solar panel on the side, sometimes attached to a tree or sometimes on the roof, and because we had no time to build masts. Yes, so we placed that there, and we placed USB charging port. Yes, now because we had to design that very fast, we had this problem that our power supply design was not very reliable. So in the first installation, we learned that when there was a lot of users connected to the access point, there was power variations that will reset the whole thing. So we have to go back into the lab at the university and improve that design. But we're, as I was explaining to the students, we need to do this with the less components because that's the only way you can get reliability.
Okay.
Welcome.
Hi, my name is Harish. I'm from Red Hat. I got a question about the software that was used for this. Are you using any of the meshing networks like Serval's, the Serval project, or any of those kinds of stuff?
Well, in the community networks in Mexico, yes, we are using meshing solutions. Yes, instead of multi-point solutions. We are starting a project in the south of Mexico country, close to Guatemala, that will be a community network built on a solution called Open Mesh. Yes, and the Open Mesh will bring a connection where, in a place where there is already a point to multi-point Wi-Fi community network, but we will put another network. In the Mexico City, there is no time to set up a mesh solution because you don't have time to tune up the network. Yes, unless the solution is quite robust, you're buying a problem rather than solving a problem. So that's why we chose point to multi-point access.
Thanks. Have you got by any chance the hardware and the network setup documented on a wiki or on a track, or
yes,
did you use mesh?
we have the document. Actually, we haven't finished the document, but yes, I will be happy to provide if you write me I can send all the details how you build this, because these are solutions that are commonly shared amongst community networks community. So it has hardware for making the masts. Yes, which routers you are looking for? You are looking for Open WRT capable routers. Yes, and how to build antennas. Yes, you want you want a lot of access with the less hardware and power, and the solar supply. We actually only made one video, which is how to use a car USB adapter to make a phone charger using a 9-volt battery and one spring from a pen. Yes, but those things we were making those documents while in the middle of the emergency.
It would be great if you would have the images and the config settings, etc. But maybe post it to the Gaia list. I think we could all learn a lot from that.
Absolutely.
Sure.
That'd be awesome if we can post it up there.
Yeah, actually, in coming out from this this emergency and related to the WTDC in Buenos Aires, we want to start a group in ISOC for not a special interest group. We want to build a team of people that have been in the middle of a disaster and put the best practice in a document. So if anyone wants to join that and provide your knowledge, that would be most appreciated for the next emergency sufferers.
I got a question about what you did. Was there any coordination with the local ham radio community within Mexico, the amateur radio community? Because they do a lot of emergency communication. They have all the skill sets, the transmitters, the radio antennas, and what have you. So I'm just curious whether any of them were involved in your in this effort.
Yeah, what happens is in Mexico City, ham radio or DX radio is becoming less used. It was more used to communicate to the surroundings of Mexico City that were really without any means of communication. And yes, they were using plain radio relays, yes, to provide information. And at the end, there were guys in the relay that would put the things in text. So that was the time we were thinking, where is all GPRS, where you can send data through DX networks? Yes, but that's the time. In the middle of the emergency, you rely on what you have.
Great.
Yeah.
I was just kidding with Harish that he took my question. Yeah, I work with the ham radio community as well. I think in certain countries, there's real competition in terms of of actually working in disaster situations. In the US, the ham radio, amateur radio, the emergency services actually appreciate the ham radio. In my case, in Canada, it's actually very marginalized. But one of the things that I'd like to suggest to you, IEEE, with its Global Humanitarian Technology group, has a very active program called MOVE, which goes into a disaster situation like in Florida and Houston recently. And it's a vehicle that they go in and they provide support, auxiliary support. So I'm just wondering if you work with the IEEE section, which is in Mexico.
Yeah, well, very fast. No, we did not work with IEEE. I know IEEE group was working in Morelos State, where it was the epicenter of the earthquake, and they were active there because that is the main area where IEEE operations go in Mexico. Yes, but we need to think back into integrating a big, large solution, considering the X radio. Yes, thank you.
Awesome. Thank you very much from Luis. And thank you for those questions. And particularly Glenn brought up and Glenn, when you do ask a question, please introduce yourself. That was Glenn McKnight. I do know him. I'm from Canada. But with respect to IEEE, ISOC is trying to work more with IEEE as are other organizations building community networks to try and also do a bit more pre-work on the disaster assistance. So the next presentation, and Arjuna, I'm teeing you up here. If you can unmute yourself, could you just let us know if you're on?
Hi, Jane. Yes, I'm on. Can you hear me?
Okay, if you could speak up a little.
Okay. Can you hear me?
I can hear you. Can people hear Arjuna? Go for it. You are on.
Right. Thank you. Thank you so much, Jane, for waking us up so early in the morning. I'm sorry that I was not able to be there due to prior commitments. Right. So good morning, good afternoon, good evening from wherever you are. I'm Arjuna Satyasiran. I'm currently at University of Cambridge. And also I'm associated with the newly formed Amber Research Labs, where I would be moving full-time starting early next year. Right. So the topic which I'm going to talk about, Jane, so can you go on to the next slide, please? Thank you. Right. So Gaia is about providing internet access, addressing the diverse set of challenges. But one of the most crucial aspects is about that you need actually physical infrastructure to solve the access problem, right? And obviously that has a whole lot of technological challenges, also regulatory hurdles and other aspects like economic aspects, which needs to be addressed, right? So Gaia has been trying to promote a whole lot of innovations in the space. There's been a lot of work by a lot of our partners and collaborators in trying to address the whole notion of bringing efficient, cost-effective physical infrastructure to solve the internet access problem. So there are several innovations in the space. So one thing which we tried to do way back in 2012 was we wanted to kind of look at solutions where some sort of innovative solutions where we could kind of say that if users have, if communities have physical infrastructure, would sharing such infrastructures with users or people or your neighbors who do not have access to internet because they're not able to afford to, would it solve some of the economic challenges that's currently there? Right, so we deployed a network called the Public Access Wi-Fi Service in a community in Nottingham. So the idea of the project was basically we wanted to kind of allow users to actually share their home broadband for free with a neighbor who was not able to access the internet using a less than best effort quality of service. So that was the context. So we were trying to investigate what were the technological challenges for doing that, as well as understanding the socioeconomic goals and incentives that is needed to make this network a success, right? So obviously the project had some interesting outcomes. We looked into new ideas of how do we come out with new business models. For example, can we enable new virtual network operators, for example, such as a local council or a charity like the Gates Foundation becoming a virtual network operator, providing connectivity in the space. We also looked at models like reverse payment models so that someone else can actually pay for users access. So these were some interesting outcomes that came out of the project, but unfortunately the project failed. The project failed because for a simple reason that there wasn't any socio-economic incentives for users to actually deploy the POS nodes and keep them alive. So if you look at the graph that I've presented on the right, that shows the POS router deployment status across a 12-month period, and you can kind of see that most of the routers that were deployed were not online most of the time. There were several reasons behind this, but one of the most compelling reasons why users turned off these routers were basically because they wanted to conserve energy. So during nighttime, users just plugged off the routers because they just switched off the routers because they wanted to save some electricity, and obviously because of the economic needs. So because you're talking about deprived areas, right? So and another reason was basically you needed these routers. For accessing these routers, you needed much better Wi-Fi coverage, and that was also one of the compelling problems that we faced, because like if a neighbor was right near a router's coverage, he was able to access the POS network, but if you're a bit further away, the coverage was really pathetic. And obviously, when you have solutions like VPN that runs on top of that, then you're talking about low data rates, and then obviously there's not much throughput you can actually get from such networks. So this has been a problem that we've faced. Jay, next slide. But on the other hand, there have been several other initiatives that have been widely successful in the Gaia space. Right. For example, community networks that have come out currently, they have been extremely successful. For example, if you take the Wi-Fi.net, which is the largest community network operator in the world, with almost.
Hey, Arjuna.
Yeah, there seems to be some problems with the audio. There's a lot of echo.
Yeah, there is an issue with the audio.
Right. Okay. So
can you just repeat what you said?
Right. Yeah, there's a lot of echo. Right. So there has been a lot of successful initiatives like the Wi-Fi.net, which is the largest community network operator in the world with almost 40,000 plus nodes, and there are approximately 100,000 users. And the success for these networks is basically because there is a much more stronger social cohesion between these communities that have made the success possible. But also there is this amazing economic compensation system that ensures that people who actually contribute as well as use a network are compensated appropriately. But obviously such compensations are more manual, and it's a cumbersome effort. So if you want to read about this, you can actually look at a SIGCOMM Gaia paper, workshop paper that we've published with the Wi-Fi.net folks way back, I think a couple of years ago. Then there are other models like the TACnet, which is in Thailand, which is run by Professor Kanchana Sud, which is also a successive community mesh combined with the WISP type model, where the network is actually tied up with the ISP for the backhaul, and the cost of the backhaul is actually amortized between the users. So there are several models. Obviously, like there are other models there are community networks that are being sprung up in Latin America, in Africa, in Asia, and other stuff. But what we want to encourage more and more such deployments, because you're talking about an approximate of 4.1 billion people who are yet to be connected. Obviously, there is not one particular solution that is going to solve this problem. But what we want to do is we want to kind of encourage more and more deployments in the space, right? So the problem is that we are trying to tackle is how do we actually incentivize network deployments at scale, especially in emerging markets. So this is a twofold talk. So I'm going to talk next few slides about some of the stuff we are doing at Amber. Leandro would be following up with some of the business models and sustainability. And interestingly, Jahan, if I'm pronouncing his name right, is also going to talk about some of the work he and this group is doing in this space. So this is a very good, this is actually a welcome change for Gaia, especially considering that there is this new proposed research group called the Decentralized Internet Infrastructure Research Group. So that could be a lot of tie-ups and potential collaborations in space. Right. So Amber is basically, you can read it as the Autonomous Modular Mesh Blockchain Router. So the idea of Amber is basically we want to build the technology, a router platform that can actually support multiple frequencies in terms of connectivity. It also has, and most importantly, it also has a payment or an economic substrate underneath, so that anyone can actually go and start deploying an infrastructure, can create mesh networks in a much more efficient way, but also ensure that these mesh networks can actually run in a more sustainable way, because there is an economic substrate underneath, right? So, Jane, next slide. Okay, there's something else missing on the left. So the idea of Amber, no, there was supposed to be some other aspect in the slide which seems to be missing. But anyway, so the Amber router is a modular platform. So you can see that there is a list of platters that can be stacked together on top of each other. So what you have is the first platter actually holds the multi-spectrum chipset. So our vision, some of the R&D work that's currently ongoing, is we are trying to plug as many wireless protocols as possible within a single chipset. So we want to support a multi-spectrum capabilities. So you're talking about supporting anything from IEEE 802.11ax to AH, and possibly other protocols that might come in, like the TV white space spectrum, LTE-U, and other aspects. So we want to support a wide range of wireless protocols in there. And you also have the other platters. So for example, if a new technology comes in that you want to kind of adopt, you don't have to kind of change the router. You just need to kind of change the platter. So that is the way we are kind of trying to bring this whole idea of modularity in terms of hardware into this game. Right. So Jane, next slide. So once we have this capability of enabling routers to connect to each other across multiple frequency bands, is we have this interesting phenomenon where we can actually have networks across diverse ranges in terms of geographical distances, right? So that means you could have multiple network operators now trying doing deployments using our Amber nodes and connecting to each other. Now, but the economic incentive here is, how do we actually make transactions happen, right? So how do we ensure that like every network operator that's actually running our network, that's running the Amber network, can make it in a much more sustainable way? So this is where we bring this whole idea of transit pricing, which like companies like Altia Mesh are actually working on. So this is something which is not obviously it's not novel. The idea is basically each and every single Amber node can actually have transactions when they actually transmit data and when they forward packets, right? So instead of anything like fiat currencies or crypto tokens, what we are saying is all this transaction happens via something from a token which is called the Amber token, right? So the idea is each and every Amber node in the network, when they transmit data or forward packets, there is a transaction that happens via the Amber nodes, via the Amber tokens. So Jane, the next slide. Jane, there seems to be a problem because most of my slides, there seems to be missing information from what I actually sent. But anyway, so one of the most important aspects is how do you actually establish trust when between nodes and between users and between participants, right? So like there is this like they say, like in the internet, no one knows that you're a dog, but in a blockchain, no one knows that you're a fridge, right? So it is extremely important to actually establish trust between this. And for this, we come out with this. We have this concept called digital identifiers. So every node and every user and every participant are associated with their own digital identifiers, and we are actually building solutions that can actually hold these digital identifiers, the private keys, in a much more safer way. So all transactions that happen would ensure that the transactions would be done via the whole concept of digital identifier. So if you want to control your router, or if you want to push firmware updates within the blockchain, within the Amber blockchain, everything is going to be governed by the digital identifiers of the users and the participants and the devices as well. So Jane, next slide. So obviously that everything has to be accounted for. So everything has to be, all the transactions have to be done. So this is going to be done via the Amber blockchain. So you have a list of metrics that I've shown on the left. Which would be logged onto the Amber blockchain. And Jane, the next slide. So one of the most critical aspects is about the consensus, right? So the current things like Bitcoin and Ethereum, which uses the proof of work, and obviously Ethereum is going to move on to a proof of stake, are like proof of work for example, has been extremely computationally intensive. So that means that there's a whole lot of issues in terms of electricity consumptions, right? So especially if you're talking about trying to build Amber's vision of trying to build the largest blockchain-based network in emerging markets and stuff, we need to take into consideration the power consumptions of the consensus protocols. So for this, we are moving away from the proof of work or the proof of stake, and we are coming out with a concept called the proof of elapsed time / proof of velocity, where we kind of build from what Intel's proof of elapsed time that has been used by Hyperledger at the moment. So we are trying to take that, and we are also trying to improvise that using an extra layer of security called the proof of velocity. I'm happy to actually talk about in the technical details of how this is done. So all of this would be in a single chip, a blockchain ASIC that will be available for anyone to use. And as I said, both the hardware and the software of the Amber nodes would be open source for the community to adopt and use. Jay, next slide. So as as Amrish was kind of pointing out, like because of all the internet transit prices and the lack of internet exchange points, like most of the content that is being served in a continent like Africa is from outside. So some of the work that we have actually done kind of showed that some of the Google caches, for example, most of the content from Google is actually served from outside the continent. So you're talking about almost 65%, whereas only 35% of the Google caches are located inside Africa. So this kind of showcases a problem where there are no proper infrastructures to actually hold local content, right? So one of our biggest ambitions of Amber, the Amber network, is not just providing connectivity in terms of the internet, but also enabling an infrastructure for having localized services. So the Amber nodes have edge computing capabilities, so that you can actually run things like lightweight OS virtualization technologies like Docker or unikernels, such as ClickOS or MiniOS or whatever you want to, onto these devices, and you can actually provide specific local services at the edges for communities. Jane, next slide. So in terms of Amber, so I kind of described this. I just gave an overall picture of what we are trying to do in terms of having a multi-spectrum chipset, having a blockchain ASIC, all governed by the concept of digital identifiers via the blockchain, which is going to be based on proof of elapsed time / proof of velocity. But the idea is the idea of the Amber Foundation and the Amber Tech group of companies and Amber Research Labs specifically is basically ensuring that we provide enough support to ensure that we are able to actually go and get deployments at scale done in emerging markets. So we are looking at new business models that can actually recover startup costs. We are also trying to work out models where we can actually start training and engaging ourselves with local initiatives. And one of the biggest advantages of having such a network or such an infrastructure is basically it gives you a lot of flexibility, so that you can have multiple local operators, local entrepreneurs who can actually emerge and start putting up infrastructure and making a business out of it, rather than actually relying on traditional network operators to actually provide you coverage, right? So that is one of the core things that we are trying to do with Amber. And especially one of the biggest advantages is the whole idea of modularity in terms of hardware, but also from the software, as well as like by having such modularity, you can actually enable new disruptive services. For example, things like peer-to-peer aid delivery is something that is now possible. We are also looking at financial services so that people can actually do peer-to-peer financial transactions rather than actually having a central authority like a bank. to actually do this. So for example, in one of our deployments in Democratic Republic of Congo, in an island called Ijwi, there are people with very few bank accounts and there are no banks, right? So the fact is, how do you actually enable financial services in these sort of communities? And this is exactly where Amber comes in terms of putting up an access infrastructure and a service infrastructure on top in a much more decentralized, distributed way. And then you can have new disruptive services like financial services that could actually pop up. And as I said, in terms of extensibility, our technology would, both the hardware and the software, everything is going to be open source for the community. So we are hoping to work with other open source initiatives like the Telecom Infra project. We are hoping to get a working group set up there. Similarly, we would like to work with the LibraMesh, Libra router folks. We've already started engagements there. And so we are open to collaborations and partnerships. And obviously, in terms of sustainability, the entire economic substrate based on blockchain enables operators to actually recover cost. And that by doing that, we ensure that there is sustainability. So next, Jane, the last slide.
Yeah, and Arjuna, we're going to have to ask you to take another minute because we need to make sure we have time for the next two presentations.
Yeah, sure. So this is the end of the slide. So as I said, we've just started. We've just finished our funding round. And now we are at the right moment where we are trying to build the technology. So as I said, it's going to be open. We are looking for collaborations and partners. So we are open for anything related to that. Thank you so much. Questions?
Okay, we have time for one question for Arjuna when I jump to the next presentation. Is someone coming to the microphone? You have to turn it on.
Stefan Batsmaya-Afnik. A common problem with every system with incentives is that routers can cheat and not declare what they really use. How do you plan to address this? Because most of the time it's addressed by closed components that the user cannot change. But if the software is open source, people can modify it and then make a router that will route but do not record properly. How do you handle this?
Okay, so if I understood the question right, so you're asking about how do you actually trust the routers are working perfectly in a simple way, because there's a whole lot of echo, and I'm not.
Did you hear the question?
Sorry, Jane.
You may be on mute. Are you on mute?
No, I'm not on mute. Hello. I'm not on mute.
Well,
can you hear me,
we can take your question. Go ahead, Arjuna.
Right. I'm sorry. There's a whole lot of echo during the presentation, and so I'm not able to really. There's a lot of echo. Okay, so basically, the entire aspect of is like it's all governed by our decentralized autonomous organization aspect that actually governs the Amber network. So the DAO would actually ensure that each and every single node that is part of the Amber network performs to what our governance models are. So we can actually have the capabilities to kind of whitelist or blacklist routers or nodes that are not actually performing based on what the governance rules have been set. So the DAO is the one which actually would ensure that all nodes act accordingly to the governance rules. Was I clear? Did you hear? Sorry, I can't hear you. Hello? Hello?
Okay. Can you repeat the explanation, because really we didn't understand it the first time.
Okay, right. So what I was saying is, like, the Amber Foundation has its own governance models which are represented by the DAO. So the network would be governed by the decentralized autonomous organization, and that would ensure that every node behaves in a trusted way, and the DAO has the capabilities to blacklist routers that do not perform that way.
But how do you detect that a router is cheating?
Yes, so we kind of actually look at how the routers are actually behaving in terms of forwarding the packets and in terms of how the payments are done. So we kind of actually have system, we'll be building the technologies to actually monitor that within the routing framework and actually detect and solve that problem. So that is one of the reasons why we are using the BMX7 routing protocol, because there are features that we could actually utilize to do that.
Do we have time for one?
Ashish Mishra from SES Networks. In this mesh network, who owns the liability for the content that's being consumed by the entire mesh?
Yes, so this is
because the internet connectivity is purchased by one.
Right. So this is an extremely interesting question that we have been debating. So we are talking about things like do net neutrality laws apply here, especially from the Amber Foundation's perspective, because we are obviously providing the infrastructure. But one of the things which we want to say is that every single Amber node is owned by the Amber network is actually owned by every single participant who actually runs the net, who owns the node, right? So what we are literally, obviously, in terms of connectivity to the internet and accessing the services, we have to stick to specific country regulations. For example, in a country like Saudi Arabia or in Thailand or in Uganda or any other places, you cannot access certain services. So we should ensure that we fulfill those requirements. But obviously, like, how do you actually govern the local services that could potentially run on the Amber network is going to be a challenging task for us, because that depends on and the whole idea of what do you say, like in terms of censorship is something which we need to kind of really address, and this is something which we need to work on. So if so we are open to ideas about this. It's something, it's a challenging task for us.
Thanks.
Yeah.
All right, thanks.
We're going to move next to Leandro, because I understand this presentation complements Arjuna's presentation. Leandro, we're going to need you to take about 12 minutes because we want to make sure Vehan has time to join. If you haven't signed on the blue sheets, please do so. And Leandro, I'm going to unmute you in about 2 seconds. Sorry for the feedback before. We're trying to fix it.
Hi, I hope you can hear me. Okay, so my name is Leandro Navarro. I'm from UPC at university and also with the joint collaboration with the Amber Research Labs. We've been working on community networks for a kind of a decade, and particularly we have working very closely with the Gifinet community network. So I'm going to talk about the self-provided connectivity. We are talking about a network like this, where we have like a basic infrastructure that is a passive one, which is trenches, ducts, fiber in case of wire connections, and also the wireless towers, links, spectrum. And then on top of that, there is the active network, which provides typically an IP service. And on top of that, of course, we have like all the applications, content, services, which are of interest of the users. So next slide, please. When we talk about why I'm talking about self-service connectivity, well, because we know that connectivity is not everywhere. One of the main reasons is because it's expensive to bring to some population, especially in remote areas or when these end users cannot afford the typical commercial prices that we find. If, metaphorically speaking, if we think in terms of like the problem of food and feeding the world, you can imagine that if everyone had to go only to restaurants, to food providers to get standard quality meals, that is ideal in one respect, but it wouldn't work unless we are, let's say, allowed or supported to prepare our own food at home. So we know that the restaurant model doesn't work for everyone, and then if we can combine the homemade model with any kind of models, when we can probably solve the problem or get closer to solve the problem. Next slide, please. So fine, the first problem for self-provision is the feasibility. Is how do we start with? How do we start with? We need to to enjoy the benefits of the internet. We need to have an infrastructure. And these infrastructures are critical for emergencies, but also critical for the daily life of the communities. They're also critical for many social benefits, but also critical nowadays for the economic activities. So you know that connectivity results more or less difficult or expensive depending on where it comes from. For instance, in our experience in one of our field work with Gifinet, the wireless came from farms 15 years ago, and it was perfectly feasible and expanded extremely, but only after there were deployments of towers, and there were a lot of local population prepared and ready for using internet services, is when the incumbents came with wireless mobile networks. Typically, when people talk about fiber is very expensive, fiber to the home. But how about fiber from the farms? If the fiber goes to the farms, that's extremely expensive. In many countries, spend a lot of money trying to do that. But when it comes from the farm, for instance, from the experience of Barn in the UK or from Gifinet in Catalonia, you can see how cheap and easy it is to deploy. So the typical problem is this initial investment in not only in money but also in human resources, in knowledge that typically can partially provided by the locals, but also typically needs some complementarity from outside. So one of the aspects we've been struggling and working with Gifinet and also now with the Amber Research Labs is how do we find efficient ways to crowdfund these contributions. Next slide, please. So there are many ways of business models. So the typical model is like a large operator that we all know. It works for a lot of population, but has limitations. There are the many small ISPs, local wireless ISPs, which also are quite successful in some communities. So they are complementary. And finally, there are the community networks where everyone can join and can expand the network and enjoy the benefits. And when you look at these models, they have differences in costs, not just because of the technology they use, but also because, for instance, when a large operator comes to a community, locals want to negotiate a good deal for the right of way. Whereas when, for instance, a friendly ISP or a community network goes, they know exactly who to talk to, and people local, they put a lot of facilities because they realize that this is their own infrastructure. Also, be careful with technology because it comes with a lot of business models embedded. So when we talk about ATM, like DSL, you need a license, you need it's a centralized model. Whereas Mesh and Bitcoin and Wi-Fi are more decentralized. And in addition, there is the issue of infrastructure sharing. If you are deploying a telecom infrastructure, you might reduce the costs by sharing it with other utilities and roads and everything. It's more complex, but it's less expensive. That's an example, for instance, of open access networks and internet exchanges. Next, please. Okay, so then once we have the feasibility, then the sustainability, as Arjuna mentioned before, there is this idea of compensating the costs and the contributions periodically that comes from the experience of GIFINet mainly. And then, well, this can be done at, let's say, this compensation can be done at costs when we cooperate, when we build the infrastructure, assuming that the benefit will come in the higher layers. In the higher layers, you find opportunities then, when the infrastructure is cheap, to create benefit, profit, even to risky initiatives that provide some voluntary or commercial services. And all that happens involving a lot of partners, like the typical consumers, everyone who uses the network, the producers, the ones, the companies or the individuals or the volunteers who expand and maintain and operate the network, and also the necessary facilitators, which are the governmental organizations, including the regulator, and also the private people that provide rights of pass to deploy the infrastructure and towers and everything. And for, of course, finally, the content and service providers. Those are also part of the equation. Next, please. So just a summary to remember, we're talking about creating like a local commons, a critical thing that provides local digital sovereignty. And on that, you can build cooperative or competitive infrastructures and services. Everyone is good for some parts and is not so good for the others. So we can need to exploit these efficiencies and avoid inefficiencies. The result is that we have a widespread infrastructure which creates local social and economic benefits, and money circulates locally, and that creates local development. So I hope you understand, you share with me that business models, governance models are critical for the expansion and sustainability of these local infrastructures. We have to be careful also with the vertical integration that comes with the choices. We are looking for openness, for separation in the choice of hardware, software, the network, and all the related things. And also, I think it might be clear if you send me some, if you have any doubts, like we can have a commons infrastructure, and then on top of that, we can have a bigger marketplace, and that's also complementary. And just a final comment, regarding the PCP, I think that we have to document everything, and not just the technical choices, but also the business models, these situations, typical patterns, metrics, because all this is very diverse, and there are many local solutions related to local characteristics, and at least we need to learn and maybe repeat more the successes and avoid repeating the mistakes too often. And I would be happy to contribute to that if that happens. Next. And that's all. If you have any question, I would be happy to answer. We have a lot of papers about many of the things that are mentioned in the presentation. Just contact me if you're particularly interested in one of the topics. Thank you very much.
Also, we're hoping to have an online meeting in December, and so this could be part of the discussion as some of the questions you might have from the discussions here. We probably have time for one question if anyone has one for Leandro. This is part of the pairing up with Arjuna's presentation. I see no questions in the room. Leandro, thank you very much to you and Arjuna. We know you've gotten up very early. And the same is for Jehan, whose presentation I'm going to put up in a sec. But any questions in the room? Okay.
Thank you.
Thank you. Gracias. Jehan, are you there? You'll have to unmute yourself.
Yeah, can you hear me?
We're going to need to have the team in the room crank up the volume a little bit. Jehan, are you close to the microphone?
Yeah, I can try something else too.
Is that better?
Okay. Much better. Thank you very much. Go for it.
Okay. So Althea, it's a project that me and go back to the me and my co-founder Justin Kilpatrick have been working on for about a year. So next slide. I wanted to show a video, but I think it's a little tough with the format here of our prototype routers. Basically, we're trying to build software that lets people create a last mile networks without a centralized ISP. And this is by routers forming what we call an incentivized mesh network and routing over several hops. So we have patches to Babel running today, which add like verification and price metrics to the Babel protocol. A few things we're not doing. We're not doing client to hotspot. There are a lot of companies doing stuff like this that have been for a while, like Fonera or Comcast Wi-Fi in the US. There are several companies right now doing this with crypto tokens as well. We focus on routers talking to each other in the last mile, not the last 20 feet. Also, we're not building hardware ourselves. There are a lot of hardware manufacturers out there, and they can probably do a way better job at that. We're a software company. We will be distributing routers just so that people won't have to flash OpenWRT themselves and stuff like that. But and also there's a lot of different situations, different antennas you want for different kind of things. If you're going different distances, whatever, and those oftentimes need to be outside. So there's no way that we could build all that stuff ourselves. We're not making a new blockchain either. There are a lot of blockchain projects right now working on many different consensus mechanisms, lots and lots of stuff out there. Right now, our code runs on Ethereum, but we are open to switching to whatever blockchain comes out that's the best. And a lot of these new projects also will run Ethereum code as well, so it won't be too hard to switch. Next slide. So I'll get into the logical architecture of this. So basically, and actually, I'll cover some stuff that wasn't in the video. So this is our protocol consists of a price metric added to Babel, route verification, and micropayments with cryptocurrency. And for micropayments, we use something called payment channels, which lets you do payments in like 200 bytes. So through this, routers can basically form a network where they can pay their neighbors to send traffic to a certain destination, sort of like the postal service. But how we organize that into a network to provide internet access, I have in this diagram. So a user node is a node where somebody's mostly putting money in and mostly consuming the internet, so the user of the internet. Intermediary node is a node that's like carrying packets over some distance. A gateway node is a node that has a physical connection to the internet. So this could be an internet exchange at a data center. It could be some kind of a regional carrier providing backhaul. It's anywhere where it leaves the Althea mesh system and goes into the internet. And the exit node is in a data center somewhere, and it's the logical connection to the internet. And there could be several of these, and these could also service several different physical Althea mesh networks. But at the traffic, and they take the legal responsibility for the traffic. I heard someone ask about that before. And then they also do something, a user node and an exit node collaborate with each other through the verification protocol to make sure that the nodes between them are not cheating in the protocol by putting probe traffic over the nodes effectively. So that's the role of the exit node. Oh yeah, next slide, that's fine. So there's a little sort of a high-level overview of the protocol, and the protocol is pretty well defined. It's all in our white paper on our website, which I'll show at the end. But so first, what happens is a router finds its neighbors, and this is not just neighbors that the router can see on its own radios inside of its box. It's also over an Ethernet cable or over a directional Wi-Fi antenna, whatever. So they're neighbor in the network, and they form authenticated tunnels with those neighbors, and this allows them to perform access control. So a MAC whitelist is not going to cut it, because you could spoof your MAC and appear as someone else. So anything that's not coming over a tunnel does not get forwarded. So next slide. So then nodes look at their neighbors, and the routing protocol has basically given them a price list for each destination, which is propagated like the routing metric is propagated, distance vector. And they look at how much each neighbor has sent to specific destinations. And then once every few seconds, they charge each other. And this happens with payment channels. Again, it's like a 200 byte payment directly between two nodes. Doesn't need to go to the blockchain, doesn't need to go to the bank. It's backed by money that's held in escrow on the blockchain. But I don't have time to get into that. But next slide. And then this is what I mentioned a few times. So it's an additional price field and distance vector protocol, Babel. Next slide. And the verification. So in distance vector protocols or any routing protocol really that exists today, nodes can very easily pretend they have better routes than they really do and say, hey, I have 10 milliseconds latency to this destination when they actually have 100 or whatever. Or they have 0 packet loss, but they actually have 20% packet loss. So the way we fight that is that, so let's say A and C are collaborating to test the nodes between them. They have an encrypted tunnel open, and over this tunnel, they're sending regular traffic and probe traffic. And if the, basically, if what they're seeing from the probe traffic does not match what was advertised by the neighbor that they're using at the time, they know that that neighbor is being dishonest. And this happens too many times that neighbor's score goes down and the neighbor is not used anymore. So it makes it not very profitable to try to cheat. Next slide. So again, you're paying to send stuff somewhere. So it's like the postal service. You put a stamp on an envelope and it gets sent to its destination. So if you order a pair of pants online, you're actually paying the online store to send the pants back to you. And Althea works in a similar way with the exit node. So A is a user node, C is an exit node in this diagram. Next slide. So the exit node pays for the response traffic. So if you're going to go on Netflix, you're going to send a request. You're going to pay your neighbor to move that request to the exit node who puts it onto the internet. And then you're also giving the exit node a little bit extra also in a payment channel, and the exit node uses that to forward the traffic back through the network back to you. Next slide. So that's a pretty fast overview, but we have a couple test deployments I'll tell you about. These will be happening in the spring because they're in colder areas in the US, so it's a little snowy there now. So in Oregon, there's a local mesh group, and they want to bring better connectivity to a small town. It's all DSL. It's very slow, almost dial-up speeds. So a woman called Deborah has a resaleable connection at her business, and she's getting together with a group of people in the community and setting up ubiquity hardware around town. And they're working on their own kind of mask designs as well. It's interesting stuff. And they're going to use Althea to reward the nodes who are part of the network. Next slide. And then Buffalo is actually a very interesting city because, well, for us, because it's got very expensive and poor internet access. But it's also got a strong community, and people are interested in new things, innovative things in Buffalo. So we've had some interest from there. So for example, guy Frank wants to sell internet to his neighbors. It's like kind of a slow, low-slung residential neighborhood. Probably pretty easy to set up, use some ubiquity gear there and maybe some Ethernet cables. And then someone else, Paul, wants to sell internet to his tenants and also work with adjacent property owners to service them as well. And then backhaul, we found someone there who, wireless ISP, they serve businesses right now, but they're interested in being able to get into the retail market without having to deal with, retail support and service by selling into this incentivized community network. Next slide. So for community meshes, this is good if they want a system which automatically compensates members for running hardware. They don't have to worry about, like, the community network itself doesn't have to worry about finding out how much people are using, charging them for it, having bank accounts, billing software and stuff like that, and basically becoming an ISP. It lets them stay decentralized and still earn some money to maintain the network. There's also that incentive for commercial ISPs to provide backhaul, which is pretty powerful. And I've been volunteering with a community network in Oakland for a few years. that's always an issue. Trying to get backhaul is on, you know, on a budget is really tough. So this is kind of a new model that we think will get a lot more commercial ISPs into providing backhaul to community mesh networks. Next slide. So for ISPs, you know, eventually we'd like everything to run on incentivized mesh softwares, but right now it's attractive to ISPs who are not doing retail right now. Like if you own a bunch of you know, cable in the ground and you're to people's houses and you're a monopoly over that, you're not going to want this. But if you if you service mostly businesses or wholesale, or you're mostly carrying stuff a little bit longer distance, then this gives you a way to sell into the retail market without having to deal with the support and stuff that's involved with that usually. And then in a lot of cases, actually, someone in the mesh network who wants to be a central node in that network may also be able to pay part of the install cost. So we're thinking specifically for apartment buildings using this. They might be willing to pay for the fiber to be spliced in if there's some nearby, as a kind of a capital improvement, and a way for them to make money for years to come. And like I said, no need to worry about supporting retail customers, because with community meshes, people like to get involved. It's really not that hard to do, and the community kind of supports itself. Next slide. So everything we do is all open source, and a lot of it is finished now. Like I said, we have 2 Babel patches. My co-founder will be in the Babel session tomorrow, I think remotely. And on our website, you can find our email address, it's altheamesh.com. And there's also a chat link in the corner, and that's where we mostly hang out. So it's a matrix room. So, excuse me. So check it out.
Thank you very much. Does anyone have any questions for Jehan? I got your name wrong before, so sorry about that.
Pretty good.
I know thank you so much to everyone that's presented today. This is part of the Gaia focus, where we're looking at different technologies, different solutions, what cool new things are out there that people are doing. We've been talking online and at the last meeting in Prague about putting a BCP together. I think, Jehan, with what you've got, the guys on the last presentations and the teams that we're presenting from Guifi, Altormundi, Zenzeleni last in Prague, but also with these here, we may have the sort of the meat for a BCP. Stay tuned. And does anyone have any questions? Because I think what we're going to try and do is have an online meeting that anyone could join, maybe at 2 different times, so we can hit Asia and Europe, but also Latin America and Canada and the United States. So any questions for us? The whole point of this is to try and look at new solutions, what people are thinking about doing. Many of us work around the world in different communities where there is no connectivity, and the whole point is to try and find some different solutions to do that. Any questions in the room? I think people are ready for the next session. Thank you for your indulgence. We may have gone over by a couple minutes, but particularly you, Jehan, to Luis, to Amrish, to Leandro, and to Arjuna, thank you very much. This is much appreciated, and I hope the people in the audience got something out of this. And thank you very much. I think that's it. Thanks for joining.